This assessment asks us to use a reaction coordinate diagram to justify the results of the figure on screen. And so here's the question we're really asking ourselves. When we make this tetrahedral intermediate, regardless of how it has formed, although this is in the saponification reaction, will it collapse to kick out hydroxide or ethoxide, and how can we justify which one of those is going to be favored? Well, let's consider pathway B first, where we kick out hydroxide. If these electrons come down, we could kick out OH minus this way. The product we're going to end up making in this reaction is we're going to reform the carbonyl, which is good, and we're going to make hydroxide, which is also fine. We could draw this reaction coordinate diagram and say that it's going to look something like that. Let's do the same thing on the other side, but instead say that we're going to kick out ethoxide, so pathway A. So I'm going to rewrite over this arrow with yellow to say that's going to happen again for pathway A, kicking out ethoxide. Now at this point, we can assume a pretty similar activation energy, and we can assume that it's going to finish at about the same spot. So those lines are intended to be equal. What have we made? Well, at this point, we've made a carboxylic acid and ethoxide. If we compare the two, the reason these are at the same point is because we've made a carbon-oxygen double bond in both, and we've produced a leaving group with a negative charge on oxygen in both. So they're pretty similar to this point. At this point, neither path A or path B is favored. What makes path A favored, though, is that in making ethoxide and a carboxylic acid, we can have a spontaneous acid-base reaction that's going to be highly favorable. So ethoxide's conjugate acid has a pK around 16. Carboxylic acid has a pK around 5. This is going to be a highly favorable reaction that we could illustrate. And just to get out of the way of the ethoxide, we'll kind of exaggerate it. It's going to come way down here. So let me extend our reaction coordinate diagram line. That's the driving force. So this first step, in terms of favorability, either group can leave. But when ethoxide leaves and we make the carboxylic acid, we end up generating a really stable carboxylate ion. That's the driving force for saponification. And that's the reason that if we want to make a carboxylic acid using saponification, we'll normally need to acidify the mixture at the end because we have to protonate this carboxylate to give us the carboxylic acid.